In this video, we will see how to calculate the symbol error rate in a digital communication system in one-dimensional input spaces for, in general, M-ary constellations. And we will do this by illustrating how to compute the symbol error rate in a 480 constellation. A 480 constellation of 4 equiprobable symbols, and the vectors representing these symbols are -3, -1, +1, and +3, respectively for A0, A1, A2, and A3. With equiprobable symbols, the decision regions are obtained by means of the minimum Euclidean distance design criterion. This means the decision region of a given symbol is given by the points closer to this symbol than to any other symbol in the constellation. And the decision regions in this case are given by 3 thresholds: a threshold at -2, a threshold at 0, and a threshold at +2. Thresholds in the middle points between symbols in our constellation. The symbol error rate is obtained by averaging the conditional probabilities of error. The conditional probability of error for the symbol A0 is Q of 1 divided by square root of N0 halves. For A1 is twice this amount. For A2 is the same one that for A1, and for A3 is the same one that for A0. Once that we have these conditional probabilities of error, the total probability of error is just the average of these 4 conditional error probabilities. Here, now we are going to see how to compute these conditional probabilities of error. We start with the conditional probability of error for symbol A0. The conditional probability of error for a given symbol is obtained by integrating out of the decision region of this symbol the conditional distribution of the observation given this symbol. In this case, the conditional distribution of the observation given A0 is a Gaussian distribution with mean A0, that in this case is -3. And the decision region for this symbol is from -2 to -infinity. This means that we need to integrate this Gaussian in the red area that we have here, out of the decision region of A0. Obviously, the probability of error, in this case the conditional probability given A0, is Q of the numerator 1, because the integral is at distance 1 of the mean of the Gaussian. The distance between the mean and the threshold is 1, and in the denominator we have a square root of N0 halves. For the second symbol, for A1, the conditional probability of error is obtained by integrating out of the decision region of this symbol the conditional distribution of the observation given A1. Now the decision region is the interval between -2 and 0. We need to integrate the Gaussian out of this interval, and now the Gaussian distribution has a mean equal to A1. In this case, the mean is -1. We have that this probability of error is 2 times Q of 1 divided by square root of N0 halves, because the 2 thresholds are at distance 1 of the mean in this case. And something similar, the same result, is going to be obtained for the third symbol. Now the mean of the Gaussian distribution is A2, which is 1. The decision region is from 0 to 2, but we have the 2 thresholds at distance 1 of the mean in the Gaussian distribution. Therefore, the integral is again 2 times Q of 1 divided by a square root of N0 halves. Finally, when we transmit A3, the last symbol, the conditional distribution of the observation given A3 is a Gaussian distribution of mean A3. In this case, the mean is 3. It is necessary to integrate this Gaussian out of the decision region of this symbol, the decision region is values higher than 2, so we need to integrate the Gaussian distribution for values lower than 2, the red area that we have in this picture, and this is given by Q of numerator 1, the distance between the mean and the threshold, denominator square root of n0 halves. With these 4 conditional probabilities of error, now the average is giving us the probability of error, the symbol error rate. 3 halves, in this case of Q, of 1 divided by square root of n0 halves. And the procedure is the same one for every constellation. It is necessary to compute the conditional probabilities of error, by integrating the conditional distribution of the observation for every symbol out of its decision region, and then the average provides the symbol error rate.